This section is on integrals and derivatives of exponential functions and log functions of non-e bases. So if you want to take the derivative with respect to x of a to the x, the way to come up with the formula for this is to change a to the x into e to the ln a to the x, because the e and the ln are inverses. Then what we can do is, since x is an exponent in this log, we can put it in front. So we have e to the x ln a. Ln a is a constant, and so basically you are taking the derivative of e to a constant times x. So the derivative of e to the x is e to the x. So the derivative of e to the x ln a is e to the x ln a. Then by the chain rule, you take the derivative of the exponent, and the derivative of x ln a with respect to x is just going to be ln a. And so that takes us to here. And so therefore the derivative of a to the x with respect to x becomes this e to the x ln a times ln a, and then I can transform this e to the x ln a back into an a to the x, so you get an a to the x times ln a. Of course, if a were equal to e, you would have e to the x ln e, and ln e is 1, taking you back to our regular e to the x rule. Now, of course, like all the other differentiation rules, we involve the chain rule with this, so if it's the derivative with respect to x of a to the u, it's the a to the u times ln a, and then again du dx, which is that chain rule piece. So here's our derivative with for e to the x, here's our derivative for a to the x. Now, knowing that derivatives and integrals are somewhat inverses, and same with exponentials and logs, we're going to see a few more rules here which are not all that surprising. This is now the derivative of a log, and so what we can do, derivative of respect to x of log a as opposed to ln x, what we can do is a change of base formula. So log x, if we don't put a number here, we assume it's base 10, but it could be any base. So log x is ln x over ln 10, and ln 10 being a constant, this is the same as ln x times 1 over ln 10. 1 over ln 10 I can put in front because it's a constant multiple. So now I've got 1 over ln 10 times the derivative with respect to x of ln x, which is 1 over ln 10 times 1 over x. So therefore, if you have a base a, what ends up happening is you have 1 over u du dx. Here's your chain rule. Here's the 1 over u from derivative of log, and you're dividing by ln a. And so if we take a look at derivatives of a to the x, we multiply by ln a. If we take derivatives of log the base a of x, we divide by ln a. And again, that's that idea of the inverses of logs and exponentials. So here's a summary of a few of these rules. Here's base e, and then if we have a base a for our log or for exponential, it gets adjusted accordingly. Now let's take a look at the integral of a to the x, and the way we handle that is in a very similar fashion to what we did for derivatives. We can rewrite a to the x as e to the ln a to the x, which I can put in front, then the x exponent becomes a coefficient. I can write it this way, ln a times x, and what I would do is I would have a u substitution where my u is ln a times x, therefore my du is ln a dx, and so what happens in red is I'd have to put a ln a here, so I need a 1 over ln a out front, 1 over ln a integral from e to the u du, 1 over ln a e to the u plus c, and that's how I end up getting all the way over to here. And then again, e to the ln a times x is just a to the x. And so integrating a to the x is a to the x divided by ln a. So again, it's this inverse idea. Derivative of a to the x, you're multiplying by ln a. Integral of a to the x, you're dividing by ln a. Of course, with your plus c being an indefinite integral. Here's a sample derivative problem. Now, as always, we try to use properties of logs whenever possible in doing these problems. So what I would do first is separate this into multiple logs. I'd factor the top as x plus 1 times x minus 1. Because they're both positive, these are positive logs. This is in the denominator, so it's negative. Differentiate each one individually. So I've got 1 over x plus 1 times 1 over ln 3 because it's a base 3. 1 over x minus 1 times 1 over ln 3. And 1 over x, 1 over ln 3. And then I just factor out a 1 over ln 3. And I've got a few fractions here. Here's the sample integral. So definite integral, integral from 1 to 10 of log base 10 of x, or log x over x. So this is done using a u substitution. U is log base 10 of x. Therefore, my du is going to be 1 over ln 10, because it's a base 10, times 1 over x. Well, I have the dx over x, but I don't have the 1 over ln 10, so I will put the 1 over ln 10 in here. And therefore, I need a ln 10 on the outside. So this is my new integral. Now I'm going to actually do my u substitution. My ln 10 stays as it is. My log base 10 of x is my u, and my dx over x ln 10 is a du. Now, because I've changed the u's, I've got to change my limits of integration. So log base 10 of 10 is 1, log base 10 of 1 is 0. So here are my new limits of integration. Got my ln 10. The integral of u du is simply 1/2 u squared. Integrate from 0 to 1. So now I've got ln 10. I've got my half. I've got 1 squared minus 0 squared, so half minus 0. And then this becomes 1/2 ln 10, or if you prefer, you can write it as ln rad 10, putting this back inside as an exponent. Just a few more examples. 3 to the 2t over t, so this is of course going to, we can use quotient rule, we take the bottom and we square it, and then write it on top, times the derivative of the top. The derivative of 3 to the 2t is 3 to the 2t, and then times ln 3 because it's a base 3, then times the derivative of 2t, which is 2, chain rule, minus the top, 3 to the 2t, times the derivative of the bottom, which is just 1, so I didn't bother writing the 1. And then you can clean this up a little bit. What I did was reordered things and factor out a 3 to the 2t. The 2 ln 3, I made a ln 9. This example here, again, I can write this as separate logs. So this 2 comes from the fact that it was a squared. It's a quotient, so I separate the difference of 2 logs, and then I've got 2 constant multiple. 1 over x is the derivative of the log. 1 over ln 2 because it's a base 2, and then minus 1 over x minus 1 and a 1 over ln 2, and you can do a little more algebra to clean that up if you want. This one's already shown, but the idea again is using properties of logs. This is a half power the squared. I'll put it in front. I can factor now. I can separate in different logs. So to this point, I still haven't done any calculus, just doing some pre-calculus to make it easier to differentiate. I've got my half as a constant multiple, derivative of the log, base 5, half, derivative of the log, the base 5, and then I can factor out the 1/2 and the 1 over ln 5 and put this back together again as one fraction. This is an example which requires logarithmic differentiation. That's because we have a variable base and a variable exponent. So the way to handle this is to take a log of both sides. So before we differentiate, take a log of the left and take a log of the right. That allows us to take this exponent and write it in front. So I've got 2 over x times ln x, which I rewrote as, well, 2 times ln x over x. Now we differentiate each side. If I differentiate the right, 2 is my constant multiple. I use quotient rule here, so take the bottom and square it, write it on top, times the derivative of the top, derivative of ln x is 1 over x, minus the top times the derivative of the bottom, so ln x times 1. The left side, well, derivative of ln y is 1 over y, but then by the chain rule, you have to take the derivative of y with respect to x, so there's your y prime. So ln y becomes y prime over y, sort of implicit differentiation. We call it logarithmic differentiation here because we had to add logs to both sides. So I clean up the right side a little bit to get to here, and finally, I have y prime over y. Well, I just want y prime, so I'm going to multiply y to the other side. So I've got my 2, I've got my 1 minus ln x over x squared. I've got to multiply this to the other side, so that's why I have x to the 2 over x over here, because that's the same as y. Here's an integral. For this one, I am going to make u 3 minus x squared, the exponent here. So my du then is negative 2 3 minus x dx. It's power rule, so I've got 2 times 3 minus x, then times the derivative of 3 minus x, which is my negative. And so I put a negative 2 on the inside, which is why I have the negative half on the outside. Now I'm going to write it in terms of u's. Negative half on the outside. I have a these pieces are all my du. This is my 7 to the u. Negative a half. The integral of 7 to the u is 7 to the u over ln 7 plus c. And then once I've integrated, I can plug back in 3 minus x squared for my u to get to this answer. Here we have 2 to the sine x cosine x dx. I make a u substitution where u is sine x. Once again, I'm going to use the exponent here as my u. U is sine x, so du is cosine x dx. Simply becomes 2 to the u du. Integral of 2 to the u is 2 to the u over ln 2 plus c. And then I end up getting 2 to the sine x over ln 2 plus c.